In our work, we will perform precision measurements on molecules, on the smallest molecules, like the hydrogen molecule H2 and the hydrogen molecular ion, like H2 plus or HD plus. In molecules, it's only the electromagnetic force that plays a role. So if we describe a full theory of electromagnetism or quantum electrodynamics, we can calculate the level structure of molecules. And these theories can be confronted with the precision measurements that we do. And if there's any deviation, that is an insight in new physics. Theodore Kaluza in the 1920s devised a theory in which he formulated general relativity in 5 dimensions. From a physical perspective then, the question arises, where is this 5th dimension, or where are the higher dimensions? Oscar Klein in 1926 came up with a solution to this conundrum. He postulated that these extra dimensions were small, very small, so small that they could not be observed. Then in the 1980s, string theories came back again to the idea of unification. They tried to design a theory of everything. And they formulated theories based on strings, but they could then make them only consistent if they postulated the existence of some 10 or 11 dimensions. Let us look at gravity. Newton postulated a law, the gravitational law, whereby 2 masses of m1 and m2 are attracted to each other with the inverse square of the distance. Immanuel Kant, the great philosopher, he already explained and understood that this inverse square law, this 1 over r square, has to do with the fact that our world is defined in 3 dimensions.
The ADD theory, named after its proponents, assumes that standard model particles and interactions are confined in our visible 3+1 spacetime, but the so-called brain is just a slice embedded in the higher dimensional bulk. Gravity is special since it can leak through the bulk, and its strength in our visible brain appears much weaker than the other forces. Although we focus now on ADD, we note that related RS scenarios were also explored in this study. As a consequence of extra dimensions, the ADD gravitational potential has a different distance dependence, related to the number of hidden dimensions and their compactification radius. For distance separations much greater than our comp, the ADD potential should be in correspondence with Newtonian gravity, thus establishing the link between the gravitational constants. For separations within our comp, the ADD potential has an extra factor over the strength of normal Newtonian gravity, depending on the compactification size.
One can test deviations from Newtonian gravity by studying the interaction of 2 test masses separated at some distance. Now one can imagine the classic Cavendish experiment where he determined the gravitational constant big G. Now the H2 molecule can then be considered as a very small Cavendish experiment where the 2 protons are our test masses and we measure the vibrational frequency of the oscillation.
In the laser lab at VU University Amsterdam, we use a huge variety of laser systems spanning the infrared to the extreme ultraviolet wavelength range, some with very high intensities. This can be continuous or pulsed in time. We use these along with tricks and techniques to perform very high precision spectroscopy on simple atomic or molecular systems. The spectroscopic results are in excellent agreement with the most accurate ab initio calculations, yielding differences well within the combined uncertainty of experiments and theory. Any effect from new physics is thus constrained to be smaller than this value.
The 2 protons in our system obey quantum mechanics, and thus their distance of separation is given by the probabilistic wave function, and thus one has to integrate the effect of the ADD potential. The effect in the transition energy is actually the difference between the shifts between 2 energy states, and thus the bigger the difference in the wave functions, the greater is the sensitivity to the ADD interaction. We present a few examples using transitions from both neutral and ionic molecular hydrogen species, setting compactification scales up to 7 extra dimensions.
Thus, for string theories that propose 11 dimensions, the compactification size must be less than 700 nanometers.
We compare our bounds to those obtained from other techniques that in general access a vastly different energy or length scale. Now, all these are complementary, and it is remarkable that this may provide possibilities to test our most modern theory that go beyond the standard model of physics.